Bismillahirrahmanirrahim. So let's continue our lesson on second half of the chapter 13 where now we are going to learn about Kepler's law and the motions of planets. Alright, so there are three laws in Kepler's laws. The first one is all planets move in elliptical orbits with the sun at one focus. And the second law is the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. The third one, the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. So what does that mean? How to apply all of this law? We're going to discuss it in detail after this. But all these three statements, all the laws must be memorized. The first one, semi-major axis. So talking about that the orbit of a planet, for a planet is in terms of elliptical orbit. Right? It's actually elliptical orbit. We can imagine, the elliptical orbit is actually a combination between two circular orbit. That is why it has two foci. This is a focus point number 1. This is focus point number 2. So one of the focus point will be empty. The other one is where the sun is. Right? And this is a path taken by the planet. For example, the Earth, right, orbiting the sun. So when we examine about elliptical orbit, we have to have the knowledge about the semi-major axis, where it has the length of the A here. This is semi-major axis, we call it. Alright, and the semi-minor axis here, has the length of B. Right? Then each focus is located at the distance C. Alright, at the distance C from the center. Then in terms of application, right? So approximately, we can say that elliptical orbit is imagined as a circular orbit is good approximation. For the case of, let's say, now we are going to consider Mercury, orbiting the sun. This is the real center of the circle. But since the real orbit is actually elliptical orbit, so one of the foci will be the sun. The other foci will be the empty point. Right? So approximately, if we consider the elliptical orbit is approximately as circular orbit, is good enough actually. So take a look on this statement. The sun is located at a focus of the ellipse. There is nothing physical located at the center, the black dot. Or the other focus, the blue dot. So this is, for example, also the orbit taken by comet Halley. So we can imagine this is also the path taken by the Earth orbiting the sun. Right? For the simplicity of calculation, we are going to take circular path or orbit as approximation for the calculation 6. Then, this is done. Cut this part. Now, Kepler's second law. Alright. By applying Kepler's second law, is actually we are going to consider conservation of angular momentum. Alright. So as we know, angular momentum must be conserved So the change in angular momentum must equivalent to 0. It means that, okay, the angular momentum is a constant when L initial is equivalent to L final. That is the meaning of the L is a constant value, right? And as we know, angular momentum is actually a cross product between position vector cross to the momentum of the object. Alright, and momentum itself is mv, right? Since the m is a scalar quantity, we can factorize it outside of the cross process here, right? So it's actually m of the planet, okay, times with the product of magnitude, because we are not considering direction, okay, we are now considering the magnitude of the L. So mass of the planet times with the product or the magnitude of R cross V. Okay, so taking into consideration of elliptical orbit just now, okay, so let's say we are considering one of the foci is sun and the other foci is empty. So now at this position, okay, to the respect of the sun, the object or the planet has R of a vector position. At this instant, okay, the planet or the object, okay, the planet here is in motion with this V, and it is attracted to the sun by the Fg, okay, gravitational force, right? And this V is tangent to the position here, okay, also known as equivalent to dr equivalent to V dt. Okay, the area swept out by the R, okay, in a time interval dt, okay, is half the area of the parallelogram here. Okay, this is parallelogram, right? So talking about the area, the change in area is equivalent to half R cross dr, okay, and dr is V dt from here. Okay, so is equivalent to half R cross V dt, where we know R cross V, okay, is L over MP. If we are considering R, magnitude R cross V is equivalent to L over mass of the planet. Okay, so substitute it here as this one, right here. Then now we can rearrange this equation into dA over dt is equivalent to L, okay, over 2mp. L is the angular momentum, mp is the mass of the planet. Okay, so in terms of daily application, if you have this value of dA, the area here, the value of it is, let's say, 1 times 10 to the power of 6. Okay, so any area, let's say area of the planet cover when it move from this to this, from this position to this position, okay, this area, okay, if let's say the value of it, the area of this also 1 times 10 to the power of 6, okay, kilometer square, let's say. Right, so the same area here representing the T taken will be the same to this T. Let's say this is T1, this is T2. T1 must equivalent to T2, since the A2 is equivalent to A1. This is the application of the Kepler second law, right? Then we're going to have conclusion. If you have the same area covered, means that the time taken will be the same. Okay, this is the application of the second Kepler's law. the third Kepler's law. Okay, we know that gravitational force, okay, is equivalent to ma, obeying Newton's second law. Alright, so mass of the planet times the acceleration experienced by it. Okay, so mass of the planet is this, and the rest of this is the A, is our A, gravitational acceleration. Okay, and since approximately, okay, the planet is good enough to be imagined that it is in circular path or circular motion, so A here is the AC. That is why we put the A is equivalent to V square over R. So for a circular path, okay, the distance traveled is the circumference. Okay, we know that V is equivalent to, okay, here is actually V is equivalent to distance traveled over the time taken. For one circular path, okay, it's 2 pi r, the circumference, over the period. Okay, because period is time taken to complete one circle. Alright, so now this V is squared, right? So everything here must be squared over R. Okay, because it's over R. Then now, okay, rearrange this equation, make the T as our unknown or title or interest. So T squared equivalent to 4 pi squared over G ms R cube. Okay, so take a look on this. Here is mass of the sun, because the story is about planet orbiting the sun. Okay, so remember, the one that has the gravitational acceleration is the sun. Okay, Fg is the gravitational force experienced by the planet due to the attraction towards the center of the sun. So the G here is the coming from the sun. That is why we use mass of the sun. So in simple, the whole things in parenthesis here is substitute or replace with a simple term, which is Ks. Okay, this is a constant. Okay, S here stand for sun. Alright, in simple, T square, okay, is equivalent to Ks over R cube. Okay, remember, Ks, if you substitute mass of the sun, if you substitute the gravitational universal constant, is equivalent to 2.97 times 10 to the power of negative 19 s square second squared over meter cube. Right, so okay, we can also replace the R if you're talking about elliptical orbit. Okay, specifically we can replace the R with the A, semi-major axis distance cube. Point to ponder here, kindly be reminded that if the story or the question talking about, let's say, moon orbiting the earth, okay, so here you have to put mass of the earth. Okay, it depends on what is the center of the motion. If here in this situation the sun become the center, then you have to use mass of the sun. If the earth as the center, then you have to replace this with mass of the earth. And the list goes on. Let's say we are talking about the Mars. Okay, some satellite, let's say, orbiting the Mars. Okay, the Mars as the center. So here you are going to substitute the mass of the Mars. Alright, so this is planetary data. Okay, you don't have to memorize this. It will be given in your exam within the list of constant. Alright, so if you see here, okay, listed here mass of the planets, okay, the mean radius, right, and then the period of revolution, the mean distance from the sun, and here is the factor. almost the same, right? Almost a constant factor. Okay, when we have t squared over r cubed. Example 13.4, right? The mass of the sun. In the opening storyline, you were wondering how to determine the mass of the sun. Now that we have discussed Kepler's third law, calculate mass of the sun. So we are going to use Kepler's third law, t squared, okay, the orbital period, equivalent to 4 pi squared over g ms a cube. Right, so since our interest is mass of the sun, okay, rearrange the equation, then substitute the rest, okay, to this equation. Here is r cube, okay, so this is the r of the sun, and then this is universal gravitational constant. Here is our t, all right, okay. Taking this all from the planetary data just now, table just now, it gives us the mass of the sun is 1.99 times 10 to the power of 30 kilogram. Right. Example 13.5, a geosynchronous satellite. Consider a satellite of mass m moving in a circular orbit around the Earth at a constant speed v and at an altitude h above the Earth's surface as illustrated in the figure given. Right, A, determine the speed of the satellite in terms of GH, RE, the radius of the Earth, and ME, the mass of the Earth. Okay, so what does that mean by geosynchronous satellite? Firstly, okay, if you refer to the term given here, geosynchronous means that this satellite always synchronized between its position to the to the respective position on the Earth. So means that, let's say, if let's say Malaysia, we send Miasat to the outer space, right, as our satellite. So the Miasat now should or must pointing to Kuala Lumpur. Okay, that is the meaning of geosynchronous satellite. The Miasat must always, okay, pointing to Kuala Lumpur. Okay, not to point to Singapore or Thailand. Right? Right. So how to do that? The orbital period of the satellite, the Miasat just now, must always equals to the spin of the time taken to spin, to complete one spin for the Earth, which is 24 hours. That must be the orbital period of your geosynchronous satellite, so that, okay, whether it's day or night or morning or evening, the satellite always, okay, pointing to the Kuala Lumpur, let's say. Right? That is the meaning of geosynchronous satellite. So we know that the FG experienced by the satellite will be MA, equivalent to MA. So FG itself is this, capital G, mass of the Earth, mass of the satellite over the R, the distance from center to center, squared. And the mass of the satellite times the AC, which is equivalent to V squared over R. Okay, so rearrange this because our interest is the V. Now we have V equivalent to square root of GM, and the R is actually radius of the Earth plus the altitude, because remember R must be from center to center. So let's imagine this is the Earth, okay, and here is the satellite. So from center to center, okay, so means that you have to add up radius of the Earth plus the h, the altitude. That is the R. Okay. Part B. If the satellite is to be geosynchronous, that is appearing to remain over a fixed position on the Earth, as I explained just now, how fast is it moving through space? How fast? So again, we need to calculate the V, right? Okay, so first thing first, okay, rearrange the equation of Kepler's third law, figure out the R, okay. So R is equivalent to square of G m of the Earth T square over 4 pi square. Square everything here. Substitute the value. This is our G. This is our mass of the Earth. Also taken from the useful planetary data or table just now. Okay, and this is the period of it. Okay, how we get this? This is actually, okay, 24 hours, okay, times 60 times 60, then it is in second, right? Then is equivalent to 4.22 times 10 to the power of 7 meter. So now, once we have the R, we may use the information of the R to calculate the V by using this formula just now. Square root of GME over R. Okay. Which gives us the V is equivalent to 3.07 times 10 to the power of 3 meter per second. Okay, so this should be the velocity, the speed of the satellite, to make sure it is as geosynchronous satellite. What if the satellite motion in part A were taking place at height h above the surface of the other planet, or more massive than the Earth but the same radius? Would the satellite be moving at a higher speed or lower speed than it does around the Earth? Okay, the answer should be higher speed, because now, based on the formula of V is equivalent to square root G ME over RE plus H, okay, if we are remaining the same R and H, okay, but more massive. So mass of the planet, okay, is more massive, okay, so it's directly proportional to the V square, right? So it's going to be higher speed. Okay. Gravitational potential energy. Okay, so talking about an object having certain distance from the center of the Earth, the Sun, okay, of course that object or satellite or whatever it is has potential energy, because it has some position from the center of the Earth or the planet considered. So change in potential energy experienced by the object, since it change in position, is equivalent to U final minus U initial. Alright, which equivalent to negative of integrand of FR dr from initial R until final R. Okay, if we rearrange this equation, we are going to have F as a function of R is equivalent to negative G m of the Earth, m of the object, okay, over the R, center to center, remember, squared. Okay, so if you're talking about delta U, or U final minus U initial, it must be G m of the Earth, m of the object, integrand of dr over R squared. Okay, because is actually constant. So the one that keep on changing is actually R. Okay, so that is why we are factorizing the GME M in front of the integrand here. Right, then doing this give us G, mass of the Earth, mass of the object, okay, where we have negative 1 over r from initial up to final r. If we substituting this value into this, then now we are going to have this as our delta u, or u final minus u initial, equivalent to negative g m of the earth, m of the object, 1 over r final minus 1 over r initial. Let's say it has changed in position. Okay, initially it is position at A with r initial, and then finally this object is positioned at B. Okay, now it has r final. Still at this location, the object is experiencing Fg towards the center of the earth. Okay, so change in potential energy due to the change of the r just now, position just now, is equivalent to this. Alright, so in conclusion, okay, in general, okay, potential energy due to the gravity, okay, of earth, okay, of the earth is equivalent to negative g mass of the earth, mass of the object over r. So what does that mean by negative here? Okay, it's actually due to this pattern of the graph. The potential energy goes to zero as approach infinity position. Okay, because if you refer to this equation or this equation, if this r is too big, way too big, okay, some amount divided by the infinity value, what will happen? Zero, right? So that is the meaning of the potential energy goes to zero. That is the pattern of the graph. Okay, as r approaches infinity, so decreasing in amount, that is why we put negative here. Okay, decreasing in amount of the u, okay, is represented by the negative here to counter that. Right, so this is specifically for the case of the earth. In general, okay, potential energy due to the gravity of any planet or object, okay, is equivalent to negative g mass of planet or object 1, okay, times with the mass of the object 2, okay, for example satellite, over the distance between them. No more square, okay, no more square, because this is u. The one that has square is actually force. Alright, so we can treat the gravitational potential energy as communication between the objects. Right, so for example, you have 3 masses here. You have mass 1, mass 2, mass 3. Okay, having r. This is between 1 and 2. R1 and 2, R2, 3, R1, 3. So since we have 3 masses, you are going to have 3 communication or gravitational potential energy between the masses, the system here. Okay, so this is potential energy, gravitational potential energy between mass 1 and 2, and then between 1 and 3, and then between 2 and 3. Okay, so to calculate the u total must be negative g mass 1 mass 2 over r12 plus mass 1 mass 3 over r13 plus mass 2 mass 3 over r23. The unit of u must be in joule because it's still a kind of energy. Example 13.6, the change in potential energy. A particle of mass m is displaced through a small vertical distance delta y near the Earth's surface. Show that in this situation, the general expression for the change in gravitational potential energy given by delta u final minus u initial equivalent to this. Okay, reduced to the familiar relationship that we are used to, which is delta ug equivalent to mg delta y. Okay, then the one that we already know just now is this one, right? Okay, so let's simplify this part, okay, if you open up this, you will have this kind of, right, to factorize it. And we know that R final minus R initial here is delta Y, okay, because this is change in position. And R initial times R final more or less to radius of the earth squared. Okay, more or less, because normally altitude is in terms of kilometers, okay, but radius of the earth is in terms of order power of 20 something, right, way bigger. That is why we put it as more or less to R earth squared. So now we have approximately delta UG is equivalent to GMEM delta Y over radius of the earth squared. Okay, and factorize this. Okay, G mass of the earth over radius of the earth squared. This is actually G, the gravitational acceleration, isn't it? Then we are going to finally simplify the equation into delta UG equivalent to mg delta Y. So this is on how actually we managed to get the formula of potential energy is equivalent to mgh or mgy. Suppose you are performing upper atmosphere studies and are asked by your supervisor to find the height in the Earth atmosphere at which the surface equation is equivalent to delta UG equivalent to mg delta Y, give a 1% error in the change in the potential energy. What is this height? Okay, so delta U surface ratio to delta U general, okay, is equivalent to 1.010 because addition, okay, error, right? Okay, then substitute delta U surface mg delta Y. Delta U general is GMEM delta Y over R initial times with the R final. Alright, so what we can simplify here, we can cancel out the mass. Okay, we are left with G, okay, R initial times R final over G, capital G mass of the earth, mass equivalent to this. This is 100%, this is 1% just now. Okay, everything already settled, this one. Okay, then open up, right? Okay, the G itself here, the G is this one. Okay, the R initial is this one. The R final is this one. Okay, then simplify the term if it is possible. Mass of the earth cancel out. Okay, capital G cancel out. So we are left with, okay, here cancel out with this. Okay, then we have RE plus delta Y over RE. Okay, so we can factorize this equivalent to 1, okay, plus delta Y over RE. So delta Y itself must be 1.01 times with the radius of the earth. Okay, so substitute the radius of the earth here. You will have your delta Y is 63.7 kilometers. Okay. Energy considerations in planetary and satellite motion. So we know that, okay, all the time mechanical energy is equivalent to kinetic plus U. So for this case, we have UG, all right, and kinetic energy is half mv squared, and our UG is negative, okay, G mass of the planet, mass of the object over R. The distance must be from center to center. If we're talking about delta K plus delta U equivalent to 0, it means that delta E is 0. Okay? It means that E final equivalent to E initial. So, from that, okay, we can have this kind of pattern of equation. This is kinetic energy initial, this is potential energy initial, and equivalent to kinetic energy final, and here is potential energy in final. Right? And we know that the Fg always obey Newton's second law, which is equivalent to ma. And our A right now is approximately AC, which is equivalent to V squared over R. Okay, so our Fg is G mass of the planet, mass of the object over R squared. And kinetic energy is equivalent to, so this is rearranged, half mv squared, okay, so this one also going to be half, right? So if we multiply this side with half, this side also must be multiplied with half. Okay, so that is what are we doing, right? So the R already cancel out. Okay, so energy now can be rewrite in terms of E equivalent to G mass of the planet, mass of the object over 2R minus G mass of the planet, mass of the object over R. Okay, for here can be simplified. If it is approximately we are taking circular orbit, then we are going to use this. If we are talking about elliptical orbit, then we are going to use A, the semi-major axis. Okay, because for circular orbit, the approximately the distance is R. Okay, example 13.7, changing the orbit of a satellite. A space transportation vehicle releases a 470 kilogram communication satellite while in a circular orbit 280 kilometers above the surface of the Earth. A rocket engine on the satellite boosts it into a geosynchronous orbit. How much energy does the engine have to provide for this boost? Okay, so first thing first, R initial must be R of the Earth plus 280 kilometers because the process starts at the altitude of 280 kilometers above the Earth's surface, which gave us 6.65 times 10 to the power of 6 meter. And delta E is equivalent to E final minus E initial. So substitute the formula of the E just now to this equation. We are going to have this pattern. Right. Substitute the rest of the information. Then we will have our delta E is equivalent to 1.19 times 10 to the power of 10 joules. Right. Escape speed. Okay, based on E equivalent to kinetic energy plus potential energy just now, okay, we are going to rearrange the equation. This is actually the E total. Okay. The E total, right? Because the E total must be R max, right? Then rearrange the equation, makes the V as our interest or topic. Okay, so we have the formula of V is equivalent to square root of, alright, 2g mass of the earth over radius of the earth. Okay, square root of everything here. So this is actually known as escape speed. Okay, so means that, okay, what does that mean? How come this equation become this? It means that whenever you launch an object from the surface of the earth with this V initial, okay, and the object going to soar off until it reach final position, okay, and stop. Okay, when it stop, confirm it won't come back. Okay, it will soar off and eventually finally stop somewhere very far from the earth's surface. So if the V final is equivalent to 0, right? So R maximum. So if you have 1 over maximum value, let's say infinity, okay, must be 0, right? This part going to be 0. Okay, then this equation going to be simplified to 2g m of the earth times 1 over RE. Then you're going to have this kind of. So the V initial just now, known as escape speed, means that the object going to escape from earth, okay, not to come back forever. Okay, that is why it's named as escape speed. So means that it doesn't matter what is the mass of the object, whether it's just a ball or it's a spacecraft, okay, if the object manage to get this value of V initial, okay, it will escape from the earth's surface and not to return anymore, because finally it will reach V final equivalent to 0. This is what we call it as escape speed. Okay, so it depends on the mass of the planet and the radius of the planet, not the mass of the object, right? Example 13.8, escape speed of a rock. Okay, Superman picks up a 20 kilogram rock and hurls it into space. What minimum speed must it have at the Earth's surface to move infinitely far away from the Earth? Right, so we know that escape speed is equivalent to square root 2g mass of the Earth over r of the Earth. So calculate, substitute the g, the mass of the Earth, the radius of the Earth. You will get 1.12 times 10 to the power of 4 meter per second squared. Okay, this is a very big amount, isn't it? It's very hard to reach this amount. Okay, you need to move this amount of meter within a second. Okay, then confirm this rock will soar off, not to return to the earth anymore. Okay, that is why we call it escape speed. So means that whether it's 20 kilogram rock, 100 kilogram rock, or a building, okay, a ton of it, doesn't matter. If you manage to get to reach this amount of V initial, confirm the object will soar off, not to return back anymore to the earth. So escape speed will depend on the mass of the planet itself. Okay, so you see here, Mercury has an escape speed of this, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Moon. Okay, so all of these, okay, vary according to the mass and radius of the planets. Okay, that's all for this part. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture. Assalamualaikum.